Hi everyone, my name is Andras Kovacs, and in this presentation I'm discussing our new results on ISW anomalies from eBOSS superstructures, which is based on collaboration with the following people and also fits into a series of papers on this topic, including observations, simulations, and theoretical approaches to study these signals. And for us, the ISW or integrated Sachs-Wolfe signal is of interest because it's a very direct but unfortunately somewhat noisy probe of dark energy in the late-time universe. And the idea is that after the matter-dominated era, where the cosmic growth structure and the cosmic expansion are in balance, this balance is broken in the presence of a dominant dark energy component at low redshifts, which, due to its extra space-stretching effects, causes a decay for the large-scale gravitational potentials, which can change the temperature of the traversing CMB photons, which pass by really large-scale perturbations, superclusters, or as in this example, supervoids. And the idea to study dark energy in particular is to study the details of the measured effect. Think of an amplitude of the imprint of these structures, let's say, and then that can tell us about the underlying properties of dark energy, being the signal a bit weaker or stronger. Now, the actual motivation for us was the repeated observation of excess ISW signals from the low redshift universe, primarily from the SDSS dataset, including the BOSS SPECS catalogs and some reanalyses. But first of all, it comes from this detection of excess signals from supervoids and superclusters detected from an SDSS LRG catalog. And our principal goal here is to check what happens at the higher redshift range using the eBOSS DR16 quasar catalog, spanning roughly this redshift range, which I will say that this is not an optimal catalog for ISW measurement, but while waiting for the bigger catalogs such as DESI of Euclid, it's already quite useful to have this sort of data sets in hand and be able to use them. Now, some people argue that these sort of anomalies are just look-elsewhere effects, and contrary to these claims, we were able to show a couple of years ago already, using the year 3 data set of luminous red galaxies from the Dark Energy Survey, that considering an independent part of the sky with a similar selection of superstructures, etc., the observed excess ISW signal is present in the data. So by looking elsewhere, we were able to, in fact, confirm these anomalies. And if one considers this as a problem to solve rather than just anomaly that eventually might go away, one way of thinking is to blame somehow the growth rate of structure, because we know that the amplitude of the temperature imprint depends on the time evolving gravitational potential, which is sensitive to any change in the linear growth rate of structure F. So any kind of tension in this respect could be expressed as an alternative value of this growth rate of structure F at the low redshift universe, which of course is inconsistent with existing other but more indirect constraints on the growth rate of structure. But for this exercise, let's just consider that this independent probe is perhaps showing us something interesting. So let's explore this a little bit. And I also wanted to mention that this remains a problem because it's not easy to solve it with the traditional techniques. So for instance, changes in the lambda CDM parameters or more exotic models such as changing the equation of state W parameter can in principle change significantly the expansion history and might even suggest a high H0 value, but and they are constrained. These models are heavily constrained, but even in principle, they don't do too much for our problem with the apparently even more suppressed growth rate than in the lambda CDM model. So we will need some more radical ideas and some other solutions. But nevertheless, what we can do already with this eBOSS dataset is to go a bit beyond the existing measurements and explore this redshift range between 0.8 and 2.2. This is a nice data set in the sense that it has a lot of quasars in this redshift range. The selection criteria are applied in order to be fairly homogeneous in the observed almost 1/10 area of the sky. And while the sampling rate is relatively low, since these quasars are not too dense as we can observe them, and this also implies a relatively low signal to noise to be expected, it's still worth checking really in this unprobed redshift range and what comes out. And in order to model this, we rely on the Millennium XXL simulation and a QSO mock catalog that we built from the already existing MXXL Halo LICO mock catalog to be eBOSS QSO like as much as possible. And on the CMB side, let's say we use the ray traced ISW map for this simulation that already exists. And as in our previous analyses, we are interested in finding the largest super voids in the quasar distribution using the so-called 2D void finder method, which is just one of the possible void finding methods, but this is what we used in previous analysis, which suggests that it's robust in a way, and also it makes comparisons easier. So given all these products, then the final step in our analysis is knowing the positions and sizes of voids. We stack them, testing the temperatures at their position by rescaling the images to be stacked, knowing their angular size. And we do the same and a little bit more complicated procedure for the actual eBOSS data set with these tomographic slices, and the voids are detected. And in fact, we determined that we are able to create 4 tomographic redshift bins. So I'm showing it here. And each of them has more or less 200 super voids in them. And this allows us to do some statistics and tomography. And then the idea is that knowing the expected lambda CDM ISW signals from these kinds of structures, given the MXXL QSO mock, and the measured signal from the eBOSS and Planck data sets, we compare these two against each other in these redshift bins and to see what comes out as an evolution. And the first result is already looking very interesting, because in our lowest redshift bin between 0.8 and 1.2, given the lambda CDM prediction for maximally about 1 microkelvin signal in the center, we see something stronger than that. And if we again think in terms of an amplitude, a rescaling amplitude for this temperature profile as a change in the growth rate parameter f, we can in principle interpret this again as a more suppressed growth rate at that redshift. Okay. So now, if we consider our next redshift beam, then overall these results are consistent both with lambda CDM and also with zero, with some indications of possibly spurious signals even further out from the actual void interior, with some positive signal here and negative here. But as I said, none of this is really significant, and here the data is consistent with zero essentially. However, it's more interesting to look at the higher redshift part of the data set, because already at 1.5 to 1.9, and even more significantly at 1.9 to 2.2, we see evidence for a sign change in this ISW signal, which is a weird scenario because it perhaps indicates some kind of anti-dark energy-like behavior or the growth of the potentials. But of course, these are, as you can see, not highly significant detections, but at least if we want to combine them and use just a single and wider beam to cover the whole second part of our data set, we can say it's like a 2.4 sigma detection of this sign change, which is what it's encoded in this red point here. Or equivalently, this is 2.7 sigma away from the actual lambda CDM prediction, which is a bit below than just the new hypothesis of no signal. So this is not groundbreaking and not super significant, but it's already suggesting that something interesting might be going on at high redshift as well. And let me just highlight the one interesting aspect, because imagine that without the tomographic analysis and the proper exploration of the data, if one just naively stacks all of these super voids together in a single beam measurement, this dotted line would be your result, right? Because whereas your data prefers a very negative ISW amplitude at high redshift, it prefers a positive enhanced amplitude at low redshift. And you can basically argue that these, well, lambda CDM is a good compromise between the two, right? But my point is basically that without the knowing what to look for or to properly explore the data set, it's easy to miss these kind of signals, and this whole business appears to be a really delicate measurement. In order to understand a little bit more of these strange signals, which we really have not seen before, opposite sign ISW signals, we asked the question, can we see evidence from the CMB lensing data set of Planck for these underdensities being real voids in the galaxy distribution, right? And actually, we were able to confirm that, as well as the low redshift super voids, also the higher redshift part of the sample, which showed the weird hotspot ISW signals, these guys also show us negative overall kappa signals, which indicates that they are true underdensities in the cosmic web based on the CMB lensing information. So, as I said, formally, we would need something like an enhanced dark energy at low redshifts, but now it's also become clear that the observed eBOSS data or these data points, all the data points, are not really consistent with the lambda CDM shape, even of the evolution of growth, right? And what we can consider is some kind of unknown model X, right? Which is some imaginary class of models which could explain this. And it's worth thinking a little bit about how or what kind of models this could be. And if we consider that this need for an enhanced dark energy, which can come with an excess expansion, which probably is related to the known problems with the Hubble constant as well. This looks like an interesting problem. But of course, in order to remain consistent with other cosmological measurements, this excess, this really suppressed growth at low redshift and excess expansion has to be compensated at higher redshifts by slower expansion rate compared to lambda CDM, and also stronger growth at higher redshift. And curiously, this appears to overlap with the cosmic noon and peak star formation and accretion activity, and also with the peak quasar activity, which is an interesting coincidence or physical effect. It's yet to be determined. But let me just mention that we are not completely in the dark about these ideas, because in fact, one proposed solution for this kind of ISW anomalies was the so-called Vera model, which is a sort of heuristic implementation of back reaction models or inhomogeneous cosmologies. And the basic idea of this modified embodied simulation approach was to split or to slice your data to different small cells of one or few megaparsec size, and follow them, depending on the local matter density, the Friedmann equations in all these little cells, and then determine the overall scale factor for the next step from the volume average of the local scale factor increments, which gives us a slightly different expansion and growth history. And it turns out that since there is this possibility that in the matter domination era, the overdensities can slow down the expansion even more, and which allows more growth. And as cosmic voids begin to dominate the volume of the universe seen at low redshift, since by definition they can increase the volume more efficiently, the sort of Model X scenario that I briefly tried to describe is also materialized in this other approach. However, it has its own problems. For instance, it overpredicts apparently the traditionally defined projected 2-point cross-correlation functions of the CMB and the galaxy density maps at the expense of trying to explain the ISW anomalies from the superstructures. So probably as it is not the solution, but it's still an interesting idea. And just to sum up, let me say that we were able to use this new eBOSS DR16 quasar catalog and the MXXL mock HLT dataset to provide the measurement of the ISW signal at redshifts higher than before, as you can see here in this gray band. And what we found was a really strange apparent opposite sign ISW signal about more or less redshift 1.5, and this is inconsistent with the LCDM model at the 2.7 sigma level. And as you can see in this plot, there is this curious trend of ISW amplitudes, not always with a high positive value, but now high negative values as well at high redshift. And this suggests that it was worth exploring this high redshift dataset. And we hope to see some further tests or confirmations of these kinds of signals from upcoming surveys such as DESI, Euclid, or JPAS. And with this, I thank you for your attention and look forward to communicate or discuss with you during the meeting. Thank you.